Nice.
Making the satellite connections.
Yes. Now everybody's quiet and paying attention. Hi, everyone.
She told me I do.
You don't need a microphone.
All right, hi everyone. Welcome to the last talk of the summer, officially. I guess next week I'll be handing the baton, the laser pointer to Han Lee for the winter series. Anyway, today's speaker is Douglas Gough, and you probably all know him. I'm just going to give a brief introduction to his persona. So, Douglas is visiting from the University of Cambridge in the UK. He is currently Professor Emeritus of Theoretical Astrophysics at the University of Cambridge. He's also Fellow of Churchill College in Cambridge, Fellow Adjunct at GILA, and Consulting Professor at Stanford University. And, okay, rather than like the 3-page long description of his career, I'm just going to point out some of his accomplishments or some of his outstanding accomplishments. So he was director of the Institute of Astronomy at the University of Cambridge from 1999 to 2004. And throughout his career, he's received a number of prizes and recognitions. For instance, he won the Hale Prize of the American Astronomical Society in 1994, the James Arthur Prize from Harvard University in 1982, is that correct?
Thereabouts, I can't remember the date.
Didn't do my research. The Eddington Medal of the Royal Astronomical Society in 2002, and the Gold Medal also of the Royal Astronomical Society in 2010. And some of the particularly interestingly named honors include the Mousquetaire or d'Armagnac in 2001, and like my all-time favorite is Her Majesty's Pioneer to the Life of the Nation in 2003. So without anything else, I'll just let Douglas do his thing. So please.
Thank you, Rebecca.
Whatever it is.
So you can see what I'm going to talk about. How old is the sun? It's an interesting question if one can get a very precise value for it. And I'm really now going to attempt or explain and attempt to get a really precise value. And the reason for wanting a really precise value is that wouldn't it be interesting to know whether the sun formed at the same time as the planets, or whether it formed before the planets, and if so, by how much? I don't think there's much chance of it having formed after the planets, but you can regard that as another possibility. And so therefore, the idea is to try to get the age to a precision that one could ask that question. And that's what I've been trying to do for some years, and I've been trying to do it mainly in collaboration with my good friend and colleague Günter Hüdeck. So much of what I'm saying today is done in collaboration with him. Let me say from the outset that it is believed that the sun condensed from the solar nebula over a timescale of something like 10 to the 7 years. And so one would really like to get the age of the sun to something rather more precise than that, say 10 to the 6 years. And I'll announce right from the beginning, in case you're going to be on tenterhooks, that we haven't yet succeeded in doing so. So what I'm going to be telling you is some ongoing research towards that aim. Now, how old is the solar system? The best measurements, and by the best I mean the most precise measurements, I should say. We don't know if they're the best measurements, but the best measurements for the upper limit to the age of the solar system are the ages of the oldest chondrules, the oldest meteorites you can find. Because the meteorites were believed to condense from the solar nebula, and as they condensed and shielded, they became rock and shielded some of the elements from the interstellar medium, the cosmic rays and everything. Some certain elements started to decay in the standard way in which you do radiocarbon dating, or radio dating, sorry, not carbon. And the particular elements that are used for the long timescales of several billion years are lead isotopes. And the best number we have, the oldest meteorite known today, the oldest meteorite known in 2010, but I think it's still the oldest meteorite known today, is 4.5682 gigayears old. So that's the number with which I'm going to use to compare the age of the Sun. But I'm not going to get the age of the Sun to 5 significant figures, as the meteoritic people have done. That is not necessarily the age of the solar system. It's a lower bound to the age of the solar system, because they might find some older meteorites some other time. This meteorite was found in northwest Africa, and that's its name. I don't know quite what that means, but they're given numbers, just like astronomers give galaxies strange telephone numbers. So the way I'm going to do it, and the only way I know how to do it to that kind of accuracy, yes? I was saying it's thought to be the order of 10 to the 7 years. But it... Oh, no, you mean how long what do you mean by the solar system? The condensation, well, the condensation into the nebula is thought to take place on a slightly shorter time scale than 10 to the 7 years, and then the condensation takes place on the time scale of about 10 to the 7 years. Exactly what the figure is, whether it's 3 or 4 times 10 to the 6 or times 10 to the 7, depends on who you talk to, because there are different theories. So that's the order of magnitude. So we'd like to do 10 times better. And clearly the meteorite people have done 10 times better in precision, but not necessarily in accuracy, because we don't know that the oldest meteorite is the age of the solar system. We think it can't be older.
But that was another question. How long does the Sun take along the Hayashi track?
10 to the 7 years. Well, 3 times 10 to the 7. That's the thermal diffusion time for the Sun. Yeah. So the only way I know now how to do it is basically the way the meteorites are aged too, through nuclear physics. The transmutation of one element to another, and the particular transmutation of any star on the main sequence is the burning, as people call it, of hydrogen into helium. So therefore, what I need to measure is how much helium has been produced in the Sun, and by knowing, as I'll come to, the rate at which that occurs, we'll get an age. That's the principle. So you do that through solar modeling, and this I've put up here, the basic principles of solar modeling. You've got some observables: the mass, the radius of the photosphere, the effective temperature, and the luminosity. And the definition of effective temperature, of course, is that flux that you would radiate as a black body. So therefore, you have this relationship here. Oh, somebody gave me one of these. You've got a relationship here between the luminosity and the radius and the effective temperature. So that doesn't count. I mean, that means that only 2 of those three quantities are independent. The mass is usually assumed. We know with extremely high accuracy the product of the mass and the gravitational constant. So the uncertainty in the mass is really the uncertainty in the gravitational constant, but that's the uncertainty in the mass today. I am going to assume throughout this talk, one can ask other questions, that the mass of the Sun has been conserved on the main sequence at least. So once the Sun did arrive on the main sequence, it was condensed. It didn't accrete any significant amount of mass, and it didn't lose any either. The amount of mass it's losing through the solar wind and the extra mass, I mean the greater rate it's believed to have been being lost by the solar wind in the early days, is still a very, very small percentage of the mass of the Sun today, and I can safely ignore that. Now, in creating the model, there are some adjustable parameters. There are really more adjustable parameters than that, but those are the only ones I'm going to talk about. So that's the abundance of hydrogen, X, the abundance of helium, and by helium I really mean helium-4, which is Y, and then the abundance of heavy elements, as they're called, which normally includes helium-3, even though it's lighter than helium-4, as Z. And their relative abundances by mass, so the sum is 1, so 2 of those are independent. In addition to that, there's what we call the mixing length. I mean, we don't understand. I don't have to tell you that we don't understand the convection. Well, you may not. You may think you understand the convection, but nobody else does. And so we parameterize it. And in the simplest of models, we parameterize it with only one parameter. You might want to parameterize it with more, But as far as the core is concerned, it doesn't matter. You muck about with the photosphere, the core doesn't know. So one parameter is good enough, and that parameter basically tells you the jump in the entropy, if you like, between the adiabatically stratified part of the convection zone and the photosphere, which determines essentially its radius. So therefore alpha, you adjust to get the radius, so you immediately fix that. I mean, they're not totally independent, but they nearly are. And then I'm adding age. Typically, people studying solar models think they know the age, and so that's not regarded as an adjustable parameter, but since I'm asking what the age is, it's obviously an adjustable parameter. So you see, if you accept that we know the mass, then there are two independent observables, and there are 1, 2, 3, 4 adjustable parameters. So I need at least 2 measurements to at least get a model. 2 more measurements, and the measurements I'm going to be considering are seismic measurements. In the old days, by the old days I mean a couple of decades ago, the subject was usually presented in a rather different way. The age was never questioned, so you didn't have to have that variable, so you only needed 1 more, and the one that was being used was the neutrino flux. And people thought they knew the heavy element abundance, so when the neutrino flux didn't come out, they called it the solar neutrino problem. It's a strange thing to have done because they measured the solar neutrino flux. They've never measured Z. So they should have called it, if they didn't like the value of Z they got, they should have called it the heavy element problem. But it didn't happen that way for historical reasons, and a mixture of historical reasons and arrogance of the people that were first doing the calculations. But the solar neutrino problem's gone away. And the reason for that is that we now know neutrinos undergo transitions because they have mass. The amount by which you can measure the transitions, which is not very accurate, is not inconsistent with solar models. I've said that carefully because the uncertainties are enormous still. But one day when the spectrum of neutrino decay gets measured more precisely, we'll come back to interesting neutrino questions again, but that's not in the immediate future. So I'm going to look for some seismic ways of measuring it. Now let me just give you an idea of what we're doing. This is a plot of the square of the sound speed as a function of the radius of the sun, through the sun. Oh, incidentally, I'm going to be considering at this stage only the spherically symmetrical component of the sun. The aspherical components, which we do have some information about from seismology, at the level of which we know them, do not affect this issue to the number of decimal places I'm going to get the age. But one day again, that will become important. And there are some physical issues related to that if I've got time, I'll talk about, mention at the end of the talk. We plot the square of the sound speed because for a perfect gas, the square of the sound speed is proportional to temperature, and temperature is something we think we can feel more. No, I'm happier with temperature than I am with the square root of temperature. So we plot the square of the sound speed. And so this is approximately something like the temperature distribution, but not exactly. And these are 2 models. The continuous line it's what we think of as our best model of the sun. If I were to plot the seismological sun on that picture, you'd hardly see the difference between that and the continuous line. And I'll show you how good that is soon. The dashed line is a similar model, but with the continuous line has got an initial heavy element abundance of 2%. I say initial, it's not the heavy element abundance that you would measure in the photosphere today, because heavy elements have been settling into the sun, and so the current value is lower than that. The other model, the dashed one, has got a heavy element abundance 30% smaller. And it's an interesting sort of number. I mean, that number was invented just for playing to show pictures, but it turns out that it's more interesting than I thought when I produced this picture. This picture is, I can't read the date, 1998. I'm not expecting you to read it. It's in the wrong color. But it turns out to be quite an interesting number. And the reason it's an interesting number is because various people starting out with Asplund have reanalyzed the chemical composition of what they think is the abundances of the heavy elements in the sun, and have got a number much like that. Initially, his number was even lower than that. So that shows you something like the difference. The biggest relative difference occurs about here. You can see this little, almost this bump. It's a discontinuity in the second derivative of the sound speed, which is what happens at the base of the convection zone. And just beneath that here is the greatest difference between those two models, which is about 8%. So looking at those two numbers, which are two numbers which are in vogue from astronomical reasons, we're thinking about an 8% variation here, and that's very easy to measure seismologically. So those are the kinds of numbers we're thinking. Okay, now I was telling you we want to measure the total amount of hydrogen consumed into helium. We know how much energy that takes. We know how much energy it takes to convert, say, a gram of hydrogen into helium. It's 0.007 c squared, where c is the speed of light, grams. So if we know how much light has come out, how much energy has come out, we know how much has been consumed. Now, the luminosity of the sun satisfies this equation to really quite a high degree of precision. Where that is the age of the sun, that is the current luminosity, and this is the luminosity as a function of time. And it turns out you can muck about with the model quite a lot, and it hardly changes this. In fact, it changes even less the integral of this integrated up to the age of the sun. One can do that integral without quite trivially, and you get this factor here. I mean, that integral, the total amount of hydrogen, of helium consumed, that's integrated over the mass, okay, is equal to this thing. And as you muck about with the parameters, this factor that multiplies, I mean, this is the luminosity times the age divided by the energy per unit mass times some factor of order unity. That factor 0.84 is hardly changes with the uncertainties in your calculation. So that's a pretty stable number. Of course, when I do the calculation, I'm going to be doing individual models, but I want to point out that at least it's right from the outset, by simply looking at this formula, you can see you've got a pretty stable thing to try to measure. So there's hope. That's the point of making this remark. Okay, now the people in evolution theory, when we seismologists came in and measured the structure of the sun, were very, very proud of themselves. Here's a picture in a paper by John Bacall and Mark Pensoneau. And he plots the difference between his model and the sun. We always plot the difference between the sun and our model so that we know how much to adjust our model to get the sun. But John Bacall always thought the other way around. His models were more important than the sun. So he used to think, how much does the sun have to adjust itself to? So this is the only picture you're going to see this way up. The others are going to be the other way up. And he plots the difference with this dashed line. I mean, it's the difference from the continuous line, and that difference you see is pretty tiny. He said, oh look, isn't it tiny compared with the size of his box? So the only thing I can deduce is the size of his box is what he thought would be the accuracy of his model, and it came out to be much better than that. So he said, isn't that great? So I took that picture, I took it off, it was a Phys Rev Letters paper, and I drew on top of it the seismological uncertainty, and I drew that on top of the continuous horizontal line. Now, except those of you with very good eyes, you can't see it. And the reason for that is that we're so much better than they are. The uncertainty is so tiny you can't see it on that picture. That's not the way we ought to be showing it. So what I'm going to do is show this picture again, but the other way up, with the scale increased by a factor of 20, so that you can actually see the difference. And these are actually 5 different measures of the difference between the sun and a theoretical model. You see the scale has gone to by a factor of 20, and these represent the error bars. And so the error bars are less than 1% of the difference between the model and John Bacall thought ought to be the right answer. So the standards are enormous. And so, but when they're expanded like this, I'm showing you 5 different representations of this difference. And the reason I'm showing you 5 different representations is just so that if you read if you read papers in helioseismology, you have to be careful about how to interpret the results. Whether or not they disagree with each other, I can't tell you. And the reason I can't tell you is because all these things, all these points, are averages over some range of the difference between the sun and the model. Now, what those averages look like, what the function is that does the averaging, the weighting function, is not available. And that's typical of these papers. And the position at which they're plotted is also not available, although I can tell you actually what they are. Now, there are 3 different people doing this, and they try to get averages that are sort of fairly localized, but they don't always succeed. Now, the ones called MJT, you might recognize those initials. It's your previous director, Michael Thompson. Those are these 3. They are plotted against the centroid of the kernel. But the other 2, the green one and the asterisk one, are plotted against the position of the kernel that the author attempted to make the kernel. And so in order to interpret that, you have to know both their psychology and their ability to actually do it. And without that knowledge, you cannot get any precise information from those other 2 curves. You will notice that the MJT ones stop here because you can't get any closer, whereas the other 2 get closer to the center because they tried to get closer to the center and failed. And I know they failed because I've been in this subject, so I know that these bits up here and those bits down there are totally unreliable. At least totally unreliable if you want to interpret those numbers as something that's localized around there. They're not necessarily wrong, because the averaging of these things here and those things down there contain kernels which are sort of fairly broad near the center, and then they've got enormous side loads up near the surface up near the photosphere, which is contributing to these numbers, which is not what we want to know about. The MJT ones are all very similar, except one of them is a bit lower than the others, but you could push it up perhaps for some reason, and there are technical reasons for knowing that you might want to push it up, but I don't want to go into those details. So what I would say now is you look at this general picture, there's a broad curve like that, which is a gross, large-scale error in the modeling of the sun. The answer to which, the reason for which, we still don't know. There's a bump here, which is immediately beneath the base of the convection zone. The convection zone has got a radius of 0.714 radius of the sun, which is about here, and that's exactly where it starts. And this, I think, and I think quite a few other people think, is a result of a circulation in the tachocline, which is the shear layer immediately beneath the convection zone, which is homogenizing the chemical composition with the convection zone. Helium has been settling. You mix the helium back up again, it reduces the helium content and therefore increases the hydrogen content of the material beneath the convection zone, and that raises the sound speed. And this can be reproduced theoretically to quite a high degree of precision. But again, there are issues there that are not quite understood. That are not quite understood. One might have some ideas about it, but again, I'm not going to talk about that. There's this enormous change here. That I think I do understand. It's because the people doing this have got the wrong radius of the sun. And I'll explain that in a moment. But they think the sun is smaller than it really is. I'll define in a minute what I mean by really. And so therefore, because it's smaller, they think that what they've measured is further out, where the temperature is lower, and therefore the sound speed is lower. And that's why this comes down like that. And this can be reproduced with an asymptotic theory. Sorry? What I mean by really, I'll come to that in a minute. Oh, why there's a deviation from 0? This is the difference. Why should this be so bad near the surface? And I'm saying the reason is because they've got the radius wrong. That's all. And up near the surface, of course, there's very little density there, so you only move the sun a small amount in proportion to its total radius, and the change is enormous. And then there's this bit. Lower here and higher there, basically, no matter whether they all show that phenomenon. And I'll come back to that too. What I want to show you first of all is, yes. So this is the region we want to think about, because this is the region where the nuclear reactions are taking place. Most of the nuclear reactions take place within 20% of the radius of the sun. Well, I say most, that's 95%. It's really even closer in that we might be more interested. So but certainly this is the area I want to investigate, and its modes, sound waves that almost propagate vertically, that are the only ones that have any chance of getting near the center, and those are the ones I have to concentrate on. So I'm going to be concentrating on those. They're modes of what we call low degree, very slow variation horizontally. We've got a spherically symmetric system. The eigenfunctions are proportional to a function of radius times a spherical harmonic, and the spherical harmonic, the degree of the spherical harmonic, measures essentially the horizontal wave number. I'm interested in with a very low horizontal wave number, low horizontal wave, high wavelengths, so that's a very low degree. So I'm interested only in the modes with a low degree. Unfortunately, the modes with low degree are the ones that have been observed for the longest, so we do have some precise measurements there. So that's what I'm going to be concentrating on. And so we can look to start with an asymptotic formula. There are techniques that I'm sure you've all heard of to try to invert, as we call it, the acoustic data to get ideas of the structure of the sun. But for the kinds of measurements I'm making, those techniques are not accurate enough. Sorry, those techniques are not precise enough. So what I'm needing to do is to actually make a model and calibrate it. That's much, much more precise than any inversion. But of course, it may not be more accurate because it depends on the assumptions of the modeling. And so everything I say is going to be dependent on the assumptions of the modeling, and in particular, it's dependent on the assumptions of the theory of stellar evolution, which I'm going to accept. So if one accepts that, and if one says, hey, look, I'm looking for the modes that penetrate the most deeply are of very high order. They've got a short wavelength in the radial direction. And so one can do an asymptotic analysis at least to get a feeling for what matters. So let me give you an asymptotic formula that's been known for a long time. It's the beginning of an asymptotic formula. I shall go further along later. But this is the frequency. I'm going to mix my notations, by the way, beware. As a physicist, frequency is omega, angular frequency, but if ever you talk to observers, they only know about cyclic frequency, which is nu. Omega is 2 pi times nu, so there are 2 pi's floating around, but I'll warn you about it. So this is frequency nu. The nomenclature is a bit like in atomic physics, in the sort of a hydrogen atom. N is the principal quantum number, and that sits here. And then little l is the degree of the spherical harmonic. I'm using L plus a half as my variable for reasons I don't really want to go into, but it doesn't make much difference. It only changes epsilon. Epsilon is a constant. A is a constant, B is a constant, nu 0 is a constant. They're constants that depend on the structure of the star, but not on N or L or nu. So they don't depend on the oscillations, they depend on the structure of the star. And so it's these quantities we want to measure. Nu 0 is just the time it takes sound to travel from the center to the surface of the star. So it's 1 over 2t. Capital T is the time it takes sound to travel from the center to the surface of the star. Not the time it takes from the lower, and the mode penetrates some distance. It's not the penetration distance, it's the center of the star. That's important. Out to the radius of the star. Not to where the mode reflects back, but to the radius of the star. And I haven't yet defined radius because Martin's waiting for it. He told me just now, because that relates to my definition of the word really. And I've just told you that those previous inversions have got the wrong radius.
R is for really.
R is for real, yes. That's why it's called R, isn't it? However, this formula assumes that the variation of the structure of the star occurs on a length scale very much larger than the wavelength. In other words, it's smooth. But it isn't smooth. And it's not smooth for 3 reasons. And here are 2 of them. This is a plot of the first adiabatic exponent for an adiabatic sound wave. I will call it gamma 1 later because I'm calling it the first adiabatic exponent. The logarithmic derivative of pressure with respect to density at constant entropy. It's a thermodynamic quantity. For a perfect gas, it's 5/3. And you see it's 5/3 up here near the surface of the star. It's 5/3 down there as you go into the star. But here it deviates from 5/3, and those are the ionization zones of the most common elements, hydrogen and helium. This bump here is the ionization of hydrogen. This little bump away from this line here is the first ionization of helium, which is all mixed up with the ionization of hydrogen. And then this is the second ionization of helium. That's the continuous line. The dashed line is just to give you a feel for it, is just a model of the star that I produced with a helium abundance of 0. So it's only got the hydrogen ionization. And so therefore the difference, so then you can see that there are 2 bumps. If you look at the difference between those 2, one for the first ionization of hydrogen, of helium, one for the second. I'll tell you about the dashed line later. So, yes? Oh, sorry. I shouldn't remind you. I should tell you. I thank you for pointing it out. I haven't told you yet. Oh, thank you. Thank you. Tau is the sound travel time from the surface of the star. Acoustic waves know about sound travel time rather than radius, and so it's better to use that as a variable. So this is the photosphere, just here. And you'll note it's not the surface of the star. It's at a depth, what I would call an acoustic depth, of a little over 200 seconds. The star is bigger, and I'll explain to you why. And the reason is as follows. If you think about how a sound wave works, take some air here, you compress it a bit, the other air falls in behind it, you let go, it expands. That pushes the air here to make it compress, which allows it to expand over there, which then later pushes it over there, and the thing propagates equally in the other direction. You all understand that, right? If there weren't enough mass here to push, it wouldn't propagate. So once you get near the surface of the star, where the density is getting very low, it can no longer propagate. And the condition for it not to be able to propagate is that the wavelength is comparable, or at least 1 over the wave number is a better thing to think about, is comparable to the scale height, the density scale height of the material. In fact, there's a factor 2 that comes in approximately, but if once those two become comparable, then the wave can't propagate. And the scale height in a star gets smaller and smaller and smaller the nearer you get to the surface. Whereas the wavelength, well, that also varies, but the point is that it doesn't vary as quickly. It will diminish, but it doesn't diminish as fast. So it gets to a point where it bashes against this equality, turns around and reflects back. And that occurs somewhere beneath the surface of the star. So let me now plot for you the sound speed as a function of position in the star very near the surface. Sorry, the square of the sound speed, of course. I always mean the square of the sound speed. And this is just radius from 6.945, 100 kilometers, to 6.97. It's a very, very thin layer near the surface. And you see, this is almost a straight line. In fact, you can go back a long, long way and it stays a straight line. It's the result you would get if you tried to write down the structure of a polytropic atmosphere under constant gravity with a constant gamma. You get exactly a straight line. So you're coming down a straight line. It deviates a bit here because of the ionization of helium and then hydrogen. And this is the ionization zone of hydrogen, so you can feel it, from 10% to 90%. Then you get near the photosphere, which is just here, at 2/3, and the sound speed suddenly drops, and then you get an isothermal atmosphere for a while, and then eventually it goes up into the chromosphere and corona. Now, the sound wave, you can imagine propagating down here, and it's around this area here where it reflects back. Now, imagine yourself as a sound wave propagating along the differential equation that tells you what to do. You're coming down this straight line, and you say, hey, the density is getting tiny. The sound speed is getting tiny. The sound speed is about to drop to 0, and 0 is a singular point of the differential equation, which doesn't permit you to go through it. Hey, I've got to turn around and go back. And it turns around and goes back at a position which depends on the singular point of the equation. It's really a fancy singular point, because the sound speed doesn't go to 0. It does this, but the wave doesn't know that. It's up here. And the phantom singular point is down here. So that's what I mean by the real radius of the star as seen by the acoustic waves, not as seen by the radiation. People studying radiation know. Here's the optical depth, incidentally. If you're studying radiation, it's a very different story, but the acoustic wave doesn't know about the radiation. It knows about the density pressure stratification. So it only knows about this continual line here, and it sees that as the surface of the star. And that's what you should think of as the surface of the star. And it's a very, very precise position. And it's about 220 seconds above the photosphere in current models. So that is what I mean by the surface of the star. That's what I mean by the real surface of the star if you're doing seismology. That answers your question, Martin, of what do I mean by real. So now let me remind you now simply what this bit does. You see it's deviating here, and it's deviating here at the sort of, it starts to deviate here long before it reflects. It reflects around here, and it sees this deviation in gamma. So it's not fitting that polytrope as well as we would like. What does it feel? Well, it feels like, and also this deviation is comparable, might even be smaller than the wavelength of the wave. So we're going to look at something else here. What do we do? Well, let me pretend it's got 0 size for the moment and tell you something that I'm sure you all know. But let's keep really simple. This is a string, a vibrating string. And the orange string and the blue string are the same string, except one of them is an overtone of the other. I mean, one is one extra node. So I've got these two strings vibrating, and I'm going to put a little weight, tie a little bead to the string here, and that's at the same position when it's vibrating at the other frequency. Now, if I've tied this bead here, assuming the bead's got positive mass, then this brown curve, or orange curve, can't look like that. You've got to make it steeper here to bring an extra force to pull it down. So what should really happen when you tie that bead on, it looks like that. You've got a greater greater force in the direction perpendicular to the original string. But now if you do that, you're no longer satisfying the boundary conditions. So I better stretch that picture to satisfy the boundary conditions, and I do that with the next curve, the green curve. And so what this bead has done is to make the cavity look bigger, and therefore this frequency's gone down. So you tie a bead to a string and the frequency goes down. Another way of looking at it is I've got more mass to have to move, and so I can't move it so fast. The blue string, on the other hand, I just happened to put the bead by accident, or not by accident, at a node, and the bead isn't moving, so it doesn't change the frequency at all. So you can see the amount by which the frequency is changed depends on the distance of the bead from the nearest node. And as you get higher and higher frequencies, I mean all the nodes move, and so you get an oscillatory variation of the frequency. So that oscillatory variation needs to be considered. So what I do now is that I'm going to take this variation in gamma, approximate it, and then use that to estimate the effect on the frequency the wiggly terms, because I need to take them out in order to look at that asymptotic formula I showed you, which is only for smooth variations. So what I'm going to do is to calculate the frequency variation due to these changes, subtract them from the observed frequencies, and then use what remains to fit the smooth asymptotic formula. Pardon? The speed of sound. The bead. The bead was a perturbation. So this is a perturbation in gamma, which is occurring on a short length space. So I'm going to consider a model where gamma doesn't vary too much, or only very slowly. Consider the difference. The variation of gamma, the difference of gamma from a smooth one, because I showed you that gamma is not a constant earlier. In the ionization zones, gamma drops. So I want to take that into account and ask the question, how much does that change the frequencies? Okay? So I'm going to do it by perturbation theory. It turns out the perturbation theory is actually pretty good. So there are two terms that I've got. What I'm going to do is I'm going to assume that the variation in gamma is a Gaussian. You saw it was dipped down and dipped again. I'm going to say approximate them with Gaussians. Yes, it's from the ionization zones, from the first and the second ionization zone of helium. So I'm going to have two Gaussians that are at the depth tau I, tau 1 and tau 2. That's the acoustic depth from the surface of the star, the real surface, not the photosphere. It's got a width delta, capital delta, and a magnitude, capital gamma. That's all. And these other factors there have just been put in to make its integral 1, but you don't have to do that if you don't want to. So I'm going to differentiate that with respect to Y, the helium abundance, because it's the helium that's doing it. And I'm going to pretend it's linear. So I'm going to pretend it's linear with respect to Y. So if I differentiate it, I just divide by Y. So it's this. And now I've just taken those two terms and put them there and there. So that is what I'm going to try and approximate that. I'm going to try to find values here that would approximate the real gamma. So first of all, how good is this? Well, let me just fit this to a solar model to see how good it is. And I've already showed you, I take the solar model and I calculate d gamma by dy and plot it. That's the continuous curve and the dotted curve. That's from the model calculating d gamma by dy at y equals 0. And the dashed curve is just from fitting those two Gaussians, just to show that you can fit the Gaussians. And the fitting is only over the continuous bit. So that's why I went on dotted. I've not fitted it there because the deviation is quite large. If I fitted it there, it wouldn't make much difference. The reason the deviation there is large is because as I'm getting deeper into the star, I'm beginning to ionize heavy elements, carbon, oxygen, nitrogen, which is depressing gamma. And I don't want to include that in this calibration because I'm only interested in Y. So that's why I stopped doing the fitting just there. But that's how well I can fit. I can now multiply that derivative by Y and find that value of Y, or at least I can actually do it for the Y of the solar model, and see how well I reproduce it. And I will show you the picture I showed you before. It's this one. And I said I'd tell you what the dashed line is. The dashed line is what you get. So by approximating with those two Gaussians, I can approximate with the model at least the continuous line with that dashed line. And I'm saying that's as accurate as I need it to at least get a representation. Having done that, I can now say, all right, I can now take that shape and I can do perturbation theory on the eigenfunctions to find out by how much that changes the frequency. That you can do analytically because I've chosen something I can do analytically. I've got an analytic approximation for the eigenfunctions. I multiply it by those Gaussians and do the integrals. And that can be done analytically. And what I end up with, and here I'm changing from nu to omega because I'm a physicist when I do these calculations, and so there are factors of 2 pi lying around. It's an amplitude, and that amplitude is directly related to that gamma, which is the magnitude of the drop, and it's related to the gamma by 1 over 2t. And you might have remembered that 1 over 2t was that parameter nu 0 in the smooth asymptotics. And it's cosine, essentially cosine of omega times the acoustical depth. So if you can measure the frequency, you can measure the depth of where it's happening. And there are two terms like that. These are from helium-2 ionization. There's another one from helium-1 ionization. There's a phase I don't quite know. And then this factor here, you see as omega starts to get large, as the frequency starts to get large, it diminishes the frequency of perturbation. And the reason for that is that as omega gets large, the wave number gets larger, the wavelength gets smaller. And once the wavelength gets comparable with the size of the helium, it starts to cancel. And so you get less. So that's what's going on there. I should point out also, and I'm not going to go into the physics, that there's another discontinuity, which is the discontinuity in the second derivative of the sound speed at the base of the convection zone, and I better include that too. So that's this bottom one, and I'm not going to say where this formula comes from, except to point out there's an amplitude, and there was a 2 omega tau omega, there's 2 tau omega there too, so that tells you the depth. There are some factors here which depends on how things recover, which don't affect things very much, and I'm not going to bother with. And this amplitude here is directly related to the discontinuity in the second derivative of the density, which is equivalent to the second derivative of the logarithm of the sound speed, because pressure and gamma are continuous. Oh, gamma is almost continuous by now, because gamma is 5/3. So what I'm ending up with is a formula for the oscillation containing two terms like the one on the top and one term like that, which I want to fit. Now, we might count the parameters. Incidentally, the whole purpose of this discussion is for understanding what aspects of the frequency tell you about what aspects of the star. So it's not actually going to depend on the precision of these asymptotic approximations. And I've showed you that they're not bad, because the final calibration is going to be done with numerical frequencies very accurately computed against the observed frequencies of the star. The asymptotics won't even show. It's not there. The sole purpose of this asymptotic discussion is for telling you which parameters, when you fit these formulae, tell you about what bits of the star. And the only bits of the star that interest me in this talk is the bits in the center that will measure how much helium we've created out of hydrogen. Well, I'm not interested in the rest for this purpose. Yeah? No, I said I won't, because I'll go on forever otherwise. Please just accept it. I've got to take it out in order to fit this. I'm not telling you how I got it. Okay, do you mind? No. So, oh yeah, that's right. So now, I showed you that asymptotic formula. So I fit those oscillations, and I'll tell you a bit about how I do that in a minute. And then I'm going to go to the smooth asymptotics. Now, the smooth asymptotics that I showed you is not good enough. I've got to go further. So these are the two terms I showed you before. I'm going to include two more. And the little s on these frequencies, which are observations, going to be observations, just represent the smooth component. In other words, I'm going to fit those other terms, which I haven't really discussed yet, take them away, and I've got a smooth one left, and I'm going to fit to that formula. Okay, now, these coefficients, A, B, C, D, E, F, G, H, I, are all independent of the oscillations, but they're all integrals of the structure of the star. Now, the only ones that matter for me today are what happens near the base of the star, which is where the modes know they've got some horizontal variation. In other words, the bit that knows about L and the bit that knows the most about L. So in this term, the bit that knows the most about L is A. In this term, it's C, and in this term, it's F. And A, C, and F are the only things I'm going to be talking about today. Well, you've got to fit this to the frequencies. You've got to calculate all those frequencies. You've got to calibrate all those terms. But I'm only going to look at those three, A, C, and F. A, C, and F are integrals over the star, and the integrand is down here. If you say alpha's a label that with 1, that with 2, that with 3, and that's the integral. That's the integrand. Okay, and see what I've got to calibrate. Epsilon 1, 2, and then 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 coefficients there I've got to calculate. We didn't do the calculation for the oscillatory part. There are 11 there too. And there's also a sort of smooth bit that comes out of the asymptotics that I haven't mentioned that gives you another few. So we're into a sort of 24-dimensional space where we've got to do this fitting, which is not trivial. It needs accurate calculations, but it also needs accurate observations, and it's only recently that the observations have got sufficiently good that you can do that. Oh, it's just a label. I'm labeling A with 1, C with 2, and F with 3, so that I can write down all 3 at once. Okay? Now, what does A look like? What is the first one? Alpha equals 1. What does that look like? Well, there it is, plotted as a function of the radius of the star. It's this thing here. There's the convection zone. There's a mess at the top. That's the base of the convection zone, and it comes down there. I've shown you 3 pictures here. So A is the integral of that function. And the 3 pictures are for 3 different ages. The continuous one is 4.5 gigayears. The dashed one is 4 gigayears, and the dot dashed is 5. So that's what happens over a whole gigayear. And I'd like to measure it, well, as best I can, but at least to 1%. So I want to measure a distance, a deviation that is 1% of the deviation. Just telling you it's not easy. Right, and now, just for 4.5 gigayears, here are the integrals for the integrands for the 3 coefficients A, C, and F. This is A, the one you've just seen. Looks a bit different because I'm only going out to half a solar radius now. And this is C, and that's F. And you see that the higher up the series you go, the more concentrated it is towards the center. So I've got 3 different measures now of what's going on near the center. So now the game is to fit all that. This is a summary of what I'm doing. This is the smooth asymptotics. These are the integrals. Now it tells you A is alpha equals 1, C is alpha equals 2, F is alpha equals 3. Okay? And you see that, you know, there are these new zeros down here. If I, instead of calibrating for A, C, and F, I calibrate for nu A, nu cube C, and nu to the 5th F, then nu comes out as a factor. And everything else in there is now linear. So that makes the calibration pretty simple. 9 of those coefficients now I can calibrate with a linear inversion. I mean, with a matrix inversion. So that's easy. The oscillatory part, on the other hand, is very nonlinear and is not at all trivial. To make it slightly easier, I consider a second difference with respect to n, the order of the mode. The modes are roughly uniformly spaced. It's a bit like a crude second derivative. So that takes out the mean value and the slope, and you only look to helps to that removes quite a lot of the junk and makes it easier to fit. So we do that. Fit those 22 parameters. So how well do we do? Well, for the oscillatory part, taking frequencies of a theoretical model, this is how well we do. The symbols are for 3 values of L, just 0, 1, and 2 here. And the continuous line is that theoretical result. But it's actually a theoretical result against this dashed line. I told you there was a smooth term, which I haven't yet fully understood, in the sense I haven't worked hard enough at evaluating the integrals. So here we've just taken a 3rd degree polynomial in 1 over frequency and fitted those 4 parameters too at the same time. And that's how well we can do the fitting with a theoretical model. What about the observations? Well, I thought the best observations for low degree modes were the Bison. That's a network organized from Birmingham around the world, and they've been going for, I can't remember now, 15 years or maybe more. So I took their data and tried to fit it. That's here. The curve looks a little bit different here from before. It's got the same structure, but the relative amplitudes are slightly different because the model wasn't exactly like the sun. And it fits, I would say it fits reasonably well. Except near here. Something's gone wrong a little bit there. And, well, there we go. Don't quite know why yet. If I could push this dash curve up a bit, it would look quite good. It would require going to more than a 3rd degree polynomial. I don't want to do that. What I'd really like to do is to understand what I ought to put in rather than just an arbitrary polynomial, and that's ongoing work. I don't know the answer to that yet. But that's how well you can do, and this continuous line is the sum of these 3 lines down here. Those are the 3 contributions. This from helium-1 ionization, that from helium-2 ionization, and the rapid one from the base of the convection zone. So Gunther, Hudek, and I submitted this paper, and the referee rejected it on the grounds that when we published this picture, we weren't using the best available data. The best available data are from the SOHO spacecraft, from an instrument called Gough. So perhaps the referee came from the Gough team. Now, I'm actually a co-I on Gough, but I didn't have the data because they wanted to keep it secret, and I wasn't going to keep it secret, and so we didn't agree with each other, and I didn't be accused of not obeying the rules, so I never had the data. So I said to the referee, the reason I haven't used the Gough data is I don't have the data, so they were immediately sent to us. And she said, well, I don't know it's she, but I can guess it's she, said that we had to replace the Bison data with the Gough data. Well, I said, well, we'll include the Bison data because she wants it, but we kept the Gough data. And then here are the Bison data. These are much better data. These are the best data in the world. And that's the fit. Now, so it turns out the theory is not terribly good because it doesn't fit those data at all well, and they're the best data in the world. It fits the Bison data, so the Bison data are probably pretty bad, and they're bad in the same way as the theory is bad, and that's why they fit so well. I suppose that's the only theory I can, that's the only reason I can find to explain that. We didn't explain it in the paper. We just made sure they were on facing pages and leave the reader to puzzle over why the best data fit so badly. So perhaps I should finish, since I don't want to overrun too much. So I'm just going to go straight to the results and not explain where the results all come from. Well, let me start off. Let me say just one thing. There's a whole set of lists here of tables. These are the parameters that we fit. ACF and this delta gamma 1 over gamma 1. The reason, incidentally, perhaps I haven't explained, I guess something I should have explained. Those three parameters, A, C, and F, tell us what the core is like. But what the core is like also depends on how much helium there is there. And the delta gamma over gamma that we measure up in the convection zone is telling us how much helium there should be there. So including that is very important because it's a very different kind of measurement. So if we include all our parameters, we get an age, we get an initial heavy element abundance, and we get an initial helium abundance. These represent errors, standard errors based upon the errors in the data, assuming that they're all independent. The calibration for age and Z are not independent, so there's a cross term here, but those cross terms are pretty small. I recommend at the moment you ignore them. And you find that the smallest error comes when you use all four coefficients. If you use fewer coefficients, you don't do as well. But if you use only coefficients that don't depend on gamma 1 over gamma 1, the errors are very, very much larger. And if you use only one of the coefficients with gamma, the error is larger, but nowhere near, not as large as these others. These are just linear fits on a grid of models, just taking one linear fit, starting with some equilibrium model. Just to convince ourselves it didn't depend too much on the equilibrium model, we used two different equilibrium models. One with a heavy element abundance, heavy element abundance of 0.02. The other one was 0.014, I think. It may have been 0.013, I can't remember. And so these are the numbers from one model, these are the numbers from the second model, and you see they're similar. But it's only a single iteration. So what we then did was to take the inferred model from these and then use that as your first trial and do it again and repeat. We did it 5 times. And we managed to get then a precision, which is not an accuracy. This is after doing each iteration. We were down to getting a variation in t of less than 0.1%. Just in the iteration. And this was for Z, similar. So I'm going to end up just showing you the final, almost showing you the final results. These are taking now 5 iterations. These are the parameters we used. One had the A, one didn't. And you see with the A, we got a somewhat smaller error for the age. The errors on the heavy element abundance, which is here, were unaffected. And this is from starting from one of the models. This was from the other. And so these are the four values of age that we've got. 4.603 on average gigayears. And let me remind you the age of the oldest chondrules, 4.57 or 4.568. So we are slightly older than the oldest chondrules. That is perhaps a little comforting, but we don't really yet have enough precision down to, I mean, this figure here is varying, and that's 1 million years. We would really like to get that figure exact. There are problems with what we're doing. There are still some uncertainties. And there are many uncertainties, and I'll just list one or two of them. One is, it's been suggested that the magnetic field in the sun over the solar cycle influences the drop in gamma. Charbonnier-Basu, who looked at this, thinks there's a 10% variation, which would give us a 10% error in our estimate of the helium abundance, which translates to something like a 5 to 6% error in the age. I think she's wrong. But at the moment, ongoing work is what Gunther and I are doing, are redoing her analysis with the latest MDI data. She used old MDI data, and she didn't do it quite as carefully as she might. And I personally think that variation will go away. There are other assumptions in the theory. There's gravitational settling. How accurately has that been mimicked in theory? We don't quite know. But the gravitational settling is pretty small near the center of the sun. And so that's probably a rather minor thing. There's the assumption that the mass of the sun has been constant on the main sequence. I'll leave you to decide how important that is. Most people assume it's constant, but there are ideas that it isn't. And there are one or two other things. And I'll just mention a couple. The first is, this incidentally is the initial value of Z. This is the surface value of Z today, 0.142. And all four of the calibrations give the same answer, 0.0142. So we plotted that here. I told you Asplund gave us a very low number. His number in time has crept up. And so this is just a horizontal line with Asplund's latest number. I know it's 2009, but he hasn't improved it since. There's a French group who started to independently do it, and they got this number here. And this is us. So we're sitting between the two. You might think, that's good. You might not. Why might you not? Well, let me remind you that the 0.013 is not terribly different from the 0.014 that we get today. This is the model. The other model I used. It's this model, the 0.021, that is right here. We're wrong here by 8%. So although our model to calibrate around here has given us a surface, we've tried to calibrate the center, and the surface heavy element abundance agrees with the observations. But we know the interior doesn't. Now the interior comes only, well, almost only, not through the equation of state, which tells you about which the acoustic waves come about, but through the opacity. And so it's an opacity issue that we've got to resolve. Are the opacities wrong? Well, that's a possibility. That's what a lot of astronomers always blame the opacity people as soon as things go wrong. But, you know, the opacity people have tried very hard. And now, I mean, from seismology in the early days, back in 1990, we found a 15% mistake in the Los Alamos opacities. But we got the Livermore people to redo it and got the two together, and we found mistakes in the Los Alamos code. But they've checked it so, the Livermore people now have checked it so hard, I find it difficult to believe there's an 8% mistake in the Livermore people, at least in this region here. Up here they could be wrong, but it doesn't matter, it's in the convection zone. Here, I think it's probably right, and so I think it's a genuine problem we have to worry about. I don't know the answer. One possibility is perhaps that during the formation of the, during the formation of the solar disk, we started to get condensations of stuff. Tended to be heavy elements, and they formed the planets. Maybe the biggest one became the sun. Is that it? So implausible? And maybe it had a fairly high chemical composition, a fairly high heavy element abundance. And then as it arrived on the main sequence, or perhaps before it got to the main sequence, finally the remaining, or much of the remaining nebula fell on top, perhaps after it arrived at the main sequence, which is lighter in heavy elements. So then what you had, the star had been through the Hayashi track, it had been totally convective and mixed up, and then after that, as it approached the main sequence, it had rained on the top something of less heavy element abundance. How on what time scale did that happen? Don't know. Supposing it happened quite fast, because these planetary people tell us it happens quite fast, then you would have had a star, like the sun, with a different heavy element abundance in the convection zone than in the interior. I mean, anything that rained onto the convection zone would all get mixed up. So now you had a convection zone with less heavy elements than the interior. And then as it went up on the main sequence, as it arrived at we know the convection zone retreated. So it could have left behind a discontinuity in the heavy element abundance. That discontinuity is stable to all the simple, at least, instabilities. Convective instability, thermohaline instability, it's stable to all those. So it might have remained, and it might still be there today. And its location would be the base of the convection zone at the beginning of the main sequence of the sun. So we could try looking for it. We could try looking for it by similar ways to which we parameterize the base of the convection. Unfortunately, the signal is only 10% of the signal from the base of the convection zone, so we need to be much more careful than I've been today. And this is ongoing work, and it's one of the things, actually, that your previous director and I have started working on this summer. So maybe in a year or so, we may know the answer. Thank you. Thank you.
I have a question.
Yes, good.
You started off by saying that it's important to get the accuracy right.
Well, you need both. Well, you can't get accuracy without precision, but...
Because you're trying to compare the age of the solar system to the age of the sun.
Yeah.
So that's the question.
Mm-hmm.
Accuracy. First,
Yes, yes.
right? Okay. And of course, the accuracy depends in large part on the assumption.
Yes.
How errors in the assumptions can propagate into the final.
Mm.
Okay. So my question is along those lines. The whole question of constant mass in the sun. I want to mention the work that I'm probably very familiar with, is Brian Wood and myself, who have estimated what the mass of the sun was going back in time by essentially integrating the mass loss rate of the sun, how it increased as you go back in time. The numbers that I recall, if you go back to about 700 million years, as far as is the sun was about 0.3% more massive than today. Okay. That's the number from my memory that I can remember exactly. When you go back further to 10 million years earlier, when the sun enters the main sequence, it's going to be larger than that, but I don't know how much larger. So the question I have is, have you done a propagation analysis of saying, what if the sun were, say, 1% more massive as it enters the main sequence compared to today? Estimate is how fast the mass is lost to get down to 1.010. How does that propagate into the errors of the age that you compute using the technique?
Well, the answer to that question, of course, depends on the rate at which the mass diminished in the early days. Yeah. And if you give me a more accurate, if you give me an estimate, I will give you an answer. Let me just say that at the beginning, mass was a bit higher, therefore the luminosity was higher, so it was burning faster. So that would make me overestimate the age.
Really important.
Oh, I know. Now, my...
You want to get down to 1 part in 1,000.
Yeah. And at that point, it matters. Yes. about the level I've got at the moment, it's just marginally mattering. So I'd be quite interested to know exactly what your curve is, because you get, at the moment, I'd made some estimates with a simple analytical power law loss of mass, and was getting numbers like 0.1% increase. Now that's big enough. That's what I'm saying. 0.1% of the age. Yes.
Oh, that's a big number
It's-
compared to the accuracy that you want.
Yes. So it's important. It's about the accuracy I've got. But, I know. I know. So I need to know about that, and I need to know conjectures, if I may put it that way, about how the mass has changed, how that affects the conclusions. You're absolutely right. And that's probably the most important of the ordinary assumptions. By the ordinary ones, I mean the ones that people most usually make. Yeah? Yeah. Well, how did the planets form? Oh, the disagreement between the two numbers I showed you in the last slide and the original number is 30% or more. That's the real, I would say that's, as an outsider, that's the real uncertainty. It's interesting that those two numbers, Caffel et al. And Aspland et al. Are that close together. I find it quite surprising. Although what is interesting is with time, they've evolved towards each other, as very often these things do. Caffel's pretty constant, I thought. Aspland's gone up quite a lot towards Caffel. Yeah, but those are both hydrodynamical models, independently computed. Right. So yeah, I know there's uncertainty. I was just showing you results.
I personally agree with people like Mark Pincinel that say that solid line is probably closer to the truth in terms of the heavy element abundance of the sun, because it's, as you said, controlled by opacity. You have to understand those opacity.
Oh, you're agreeing? I said that too. Yes. Well, that's comforting. Yeah. Yeah.
And those capacities being dominated by oxygen at that critical place, and it's hydrogen and helium like oxygen. So those capacities should
That's what one would do. Yeah. So what that means, you see, is that our calibration has given us a wrong number. Because we've got a number which I was just really showing it as interesting that it agrees with Aspect and CAFAR, but it does not agree with that, which is why I showed you this picture, because we haven't got there. So now you have to ask the question. Of course, there isn't really an answer to that question without any more information. You've done a calibration, and your model doesn't fit all the data. So what does it mean? It's not clear. We've done the best we can at looking at the most data. What's commonly done, of course, you just do one thing and say, hey, look what I've done. That's not honest. So I'm trying to be honest and saying, look, we've got a number. We've got a number that's got a certain precision, which I showed you, but I don't believe that's the accuracy because of this problem here. So we've still got a long way to go. But we have to find, as best we can, some reason that will bring everything together. And my suggestion at the end, if I may go backwards through your comments, was this particular one about the possibility of the evolution of the sun towards the main sequence taking place on a timescale somewhat shorter than the eventual dispersion of the solar nebula. The planets have been taking heavy material from the solar nebula to make the planets, leaving behind something which is deficient in heavy elements, which I'm saying, could that have just rained onto the surface of the sun? If it did so, towards the end of what you might call the Henry approach to the main sequence, once the star was no longer fully convective, it would only have contaminated the outer 2 or 3% of the sun. So that contamination is easier. You're not contaminating the whole sun, so you don't need so much stuff. So I'm just suggesting that as a possibility. And I know it doesn't go totally with standard ideas of formation of systems, but I've spoken to people who are in that subject and asked them carefully, what are the uncertainties in what you're saying in terms of timescales? And this is, if you make them honest, the uncertainty is big enough that this is not ruled out. But I'm not saying it's likely. I can't think of any other reason at the moment. Oh! Oh, yes. Absolutely. That goes the wrong way. I don't want too much of that.
Just wanted to mention that these same techniques have now been used on other stars, not to calibrate the age, but to use the parts that you were just getting out of the way.
I know.
Things like the convection depth and the
Sure.
helium aspect.
Sure, that's right.
And it's been done now for bright solar analog.
But there are problems there, which I'll talk to you about later. They may not be that important for many of the calibrations. I mean, to the surface convection zones, size of convective cores, I don't think that's harder. I don't think that's been well done yet. And then fitting with stellar evolution, I don't understand. What I mean by that is I've never got my hands dirty doing that, and you never understand anything until you get your hands dirty and realize what the mistakes really are.
I just noticed that your calibration models, the helium mass spectrum, seem comfortably close to the primordial value. Not very much above that. Is that something we should be concerned with?
I've spoken to people studying the galactic evolution of the chemical elements, and they're not too concerned about it. They say that's within the realm of the uncertainties in those ideas. Yeah, so that doesn't worry me at the moment. That's true, but I'm not using that. The point is those surface terms influence. I don't know if you remember the formula. Perhaps if I go back a couple, Not sure how far I have to go back. Can't be too far away. There it is. The what you're talking about influences the parameters epsilon, b, e, and I. And although I have to fit them, they really don't. They're really almost decoupled from the parameters a, c, and f. It's only a, c, and f I'm using. You see, they might make a big effect on the value, the absolute value of the frequency, but I'm looking at aspects of the functional form of the frequency with respect to n and L that mimic more particularly the center of the sun. That's why you have to go through all this, because you have to find a signature that is mainly telling you something about the sun, which is where you want to look. If I wanted to know about the surface atmosphere, I wouldn't look at A, C, and F. I'd look at epsilon, B, E, and I. They're the ones I'm using, yes. Well, they're almost independent. I mean, it depends what you mean. How are you going to get the surface to the center? Through the evolution theory, and then what assumptions you're going to make. If you just look at the basic structure of the sun today, they don't really affect each other at all. One thing I was going to say, but didn't, but I'll say it now, is that I did point out when I showed you the difference between the sound speed in the sun and the sound speed in the model. There was this, you know, as the sound speed up, it tips down like that. But up here a bit high, near the center is a bit low, which means that the sun, this for decades now, variation of the in the center of the sun is actually smoother than models. Now, it suggests to me that there might have been some degree of mixing. Not necessarily turbulent mixing, maybe large-scale flow, because we're just measuring the spherical average. Now, if that's the case, then just taking A, C, and using them as independent parameters is not the right thing to do. It's something to do, because it's telling us about. It's not the best thing to do. The best thing to do is to take that combination of A, C, and F that most closely mimics the integral of the variation of through the center, because that's a direct measure of the amount of helium that's been produced, which is a direct measure of the age. And I've started doing that. Had I known how hard it was going to be, I might not have started. Because it turns out you've got to do an expansion of the structure of the star and how it depends on all the uncertainties, because I'm not using stellar evolution now, I'm just trying to expand everything in powers of the radius of the star, and you have to go up, and if you've got reasonable, you've got to go up to get a reasonable combination up to the 10th power of R. It's not actually, I'm making it sound too bad, it's actually expansion in R squared, it's only the 5th power of R squared. But that's 6 terms. And it's a very nonlinear system. So each term in the expansion magnifies the number of terms, I'm not quite sure how much. So I've now got 15 pages of very closely packed algebra, and I'm about 2/3 of the way through it. But having invested so much time, I intend to finish it. Then you take that combination of ACF and redo this calculation. You'll get a more precise result, and I expect that it will also be more accurate. Yes, yes.
As a function of age?
Yes, yes.
Okay. Let me send you an email telling you as much as I know.
Okay.
What I don't know.
Yes.
Okay. And what's your email address?
Douglas
Yeah.
at AS